Thanks for coming to the final session of the workshop here. To take it away, I'd like to introduce our speaker, Bryon, who'll be talking about new approaches to causal representation learning. The time is yours.
All right. Thanks for the introduction. Thanks, everyone, for hanging out to the last session. Hopefully, we've saved the best for last. The original title of my talk was this, but while I was making the slides, I realized a better title in hindsight would be this. So we're going to talk about one particular approach to causal representation learning. So before I jump into sort of the formalism, let me make sure that we're kind of all on the same page as to what the high-level goal here is. What is causal representation learning? So the idea is, in many applications, you're interested in learning causal relationships, but the measurements that you've made, talking about causal relationships between the measurements themselves, doesn't really make sense. So canonical example of this would be something like images, where we don't like to talk about causal relationships between pixels. One pixel doesn't really cause another pixel. But there are some high-level concepts, latent variables, that can be inferred from these pixels. And what's going on in that latent space might be of interest. And I should emphasize here, the word provably here is very important. There's been a lot of work on causal representation learning. And I'm going to particularly focus on proving things about identifiability and estimation of these models. So before I jump into the model, I want to distinguish between sort of two important problems that we've talked about both of these throughout this workshop. So the sort of classical problem with latent variables and causal models is confounding. So in confounding, the type of question you're usually asking is how do unmeasured confounders affect the inference of causal effects between observables. So typically you're interested in what's going on between the observables, and the existence of unmeasured confounding complicates this story. In the setup that I'm going to be talking about here with representation learning, causal relationships between the observables are not particularly meaningful. And this is the setting we're going to be talking about. So I just want to make that distinction upfront clear, that there are extensions of this that could be applied to confounding, which would be very interesting, but I'm going to focus on this setting of representation learning. So I think most folks here are familiar with the basic setup of Bayesian networks and graphical models. So just real quick to sort of set up the notation. I have a random vector X. I associate the vertices of the graph with this random vector. I have the parents and the children in that graph. I will call it a directed acyclic graph if it has no directed cycles. And down here at the bottom, we have this sort of classical factorization criterion, which gives us the definition of a Bayesian network. So if you have a directed acyclic graph in a distribution that satisfies this factorization criterion, then we call it a Bayesian network. Okay? So for today's talk, instead of thinking of the vertex set as just sort of one random vector, we're going to partition it into, of course, observed and hidden states. I'm going to assume throughout this talk that the observed variables are continuous. This is not crucial. You can make them discrete. But for simplicity, I'm going to restrict my attention to the continuous setting. And crucially, so this is important, I'm going to assume that the hidden variables are discrete. And the reason for this, which I will have a lot more to say about, is that when the hidden variables are discrete, we induce a finite mixture over the observables. And the structure in that finite mixture is going to be very important to us. And the crucial structural assumption that sort of distinguishes this from the sort of classical confounding setting is I'm going to assume that the observables have no children. There's no edges pointing away from the children. So this is what encodes this idea that the measurements don't have causal effects themselves. And under these assumptions, I can decompose this graph or partition it into two components, gamma and lambda. So gamma is the directed bipartite graph that points from H to X. So that's what I have in blue on this graph. And then lambda is the DAG over the latents, what I'll call the latent DAG or the latent causal graph. That is the edges between the latent variables themselves. At any point there are any questions about the setup or anything, please just jump in. Yeah, Dan, go ahead.
Just to clarify, does each H have to be a parent of each X, or can H's?
Yeah, no, absolutely.
Relationship between H's and X's is arbitrary.
Yeah, I'll have a precise assumption on what the relationships are. In this example, that I just randomly chose to draw it that way.
Okay.
Yeah, no, that's a good point. Okay, so the goal is to learn the hidden variables H, the latent distribution P of H, and most importantly, the graph lambda over the hidden variables. That's my goal. I'm going to focus mostly on this middle piece, learning the latent distribution, and we'll see why in just a second. I need to emphasize up front that the structure of H here is assumed to be entirely unknown. I don't know how many hidden variables there are. I don't know the size of the state spaces, and I don't know any of the relationships between the hidden variables. Okay? My goal is to figure this out just from the observed data. We don't have any interventions, and this model is also known as the measurement model. So I'll talk about previous work in just a second, but I am far from the first person to think about this model. This model has appeared in many applications as well as in the causal inference literature, the causal discovery literature. Yeah, go ahead.
If I was a really causally allergic person, would I be okay would I be able to conclude from the slide that I could just think of this as a statistical mixture model without any causal baggage at all?
Yes.
Because there are no interventions here. It's just some graph.
Yes.
Okay,
Yes.
got it.
You are correct. Yes. Other questions? And that perspective is actually going to be pretty important. That's kind of part of the perspective we take here. Okay, so like I mentioned, this is a sort of very well-studied problem. So in fact, you can think of this as sort of a generic latent variable model. Recently, this has kind of gone under the guise of identifiable representation learning. So there's a lot of renewed interest in the machine learning and artificial intelligence literature. I have to stress that this is an extremely old topic that dates back to the 1800s. So we talk about mixture models, factor models, hidden Markov models. There's a ton of literature that I will not be able to do justice to here. So I will first focus on the literature that's closest to this paper. So there's a bunch of work. The oldest one that I found is 2006. Please feel free to point out to me if there's something before that on linear models in this setting. So it's the same structure that I showed in the previous slide, but everything's linear. There's also recently been a bunch of work in the deep generative modeling literature on known structure. So the idea here is that if I go back to this slide, you assume that you know the structure of this graph, and the goal is to learn some type of deep generative model, some non-parametric model that respects the graphical structure here. So there's been some work there. Ankur talked about Boltzmann machines previously in this workshop, so that's also very closely related. And of course, in the previous workshop, Frederick talked about causal feature learning, which is sort of inspired by very similar questions that I'm focusing on here. So what do we do here? So the key sort of interest of ours is to figure out whether it's possible to identify and estimate these graphs in a very general non-parametric setting where we make no parametric assumptions. Really, the only assumptions I'm going to make are that this distribution is Markov with respect to the graph, in addition to some non-degeneracy assumptions. So we'll talk a bit more about those on the next slide. But these are things like positivity, that you have to have distinct conditional distributions, things like this, that without, you can very easily show that this problem is ill-defined. And I'll briefly talk about, so the proofs are constructive. They do, in fact, lead to efficient algorithms. So what's sort of the main assumption we're going to need to make here? So in addition to things like positivity, I'm going to make this subset assumption. So Dan, this is sort of getting to your point, that for any two distinct hidden variables, the children of one hidden variable cannot be a subset of the children of the other hidden variable. So over here on the left, you can see an example of a causal graph that satisfies the subset condition. Here in the middle, this is violated because H3 has X3 as a child, and that is a subset of the children of H2. For those of you that are familiar with the topic modeling literature and this anchor words assumption, that looks sort of like what we have over here on the right. This assumption generalizes that. It is weaker than the anchor words assumption that has appeared in the topic modeling literature. And all of these assumptions are necessary. We show in the paper, I won't go into the details here. If you break any one of these assumptions, then you can show that this graph and this distribution cannot be identified without some other assumptions. Okay. All right, so if there's nothing else you get from this talk, okay, it's this. So the basic idea behind the proof and the result that I'm going to show is that we can reduce this hard problem of learning a latent causal graph to two very well-studied problems. I don't claim that these are easy problems, but they are well-studied and we know a lot about them. So first is mixture models. And second is causal discovery. And I should emphasize here that I mean causal discovery without any latent variables. So fully observed causal discovery. If you know how to do these two things, then you can solve the problem that I've given here. All right, so how does this work? So the key fact here. So this is why I need to assume that H is discrete. If H is discrete, then it induces a finite mixture model over the observables, like you see here. So here I'm summing over all of the different multi-dimensional states of H, and I get a mixture model over X. If I take any subset S, so this is some important notation I'm going to use in the sequel. So if I take any subset of the observed variables, I could look at the induced marginal mixture, so just condition on the hidden states, and just focus your attention on the observables in S. I'm going to call the number of components in that induced marginal mixture K of S, and I will denote its weights by pi of S and the components themselves by C of S. So the key idea here is that if I look at these mixtures over small subsets S, so the sort of name of the game is to restrict S to be somehow a small subset, this is going to reveal everything that we want to know about the hidden variables. It's going to tell us the number of hidden variables, their state spaces, their relationships, and their distributions. That's kind of the key idea here. Okay, now this assumption is going to sound like cheating, but let me explain what's going on here. So the key sort of reduction that we're going to make is I'm going to assume that I have access to an oracle that gives me this mixture here. Why do I make this assumption? Okay, so understanding mixture models and their identifiability is very well studied. This is a sort of separate question. Leonard talked about this in great detail. I'm going to sort of offload that part of the problem to what is known about mixtures. And I'm going to talk, if we have time, towards the end of the talk, some of the recent work that we've been doing on this problem. So I'm going to assume access to an oracle that takes one of these subsets as input, and it's going to tell me the number of components, the weights, and the components themselves. I'm going to call this a mixture oracle, and note that the existence of a mixture oracle is equivalent to these mixtures being identifiable. As long as the mixtures are identifiable, I am guaranteed to be able to define such an oracle. Does not mean such an oracle would be efficient if implemented, but it certainly would exist. And I'm going to come back to some of these examples later on in the talk. So for now, let's just assume we have access to such an oracle. And the main theorem that we prove is if you assume these non-degeneracy conditions, the subset condition that I showed you before, and access to this mixture oracle, then both gamma, the bipartite graph from the hidden variables to the observables X, and the latent distribution P of H, these are both identifiable. And so since identifiability has been discussed previously in this workshop, I should emphasize that. So here, what I mean is that this is a one-to-one mapping. I'm not necessarily assuming that this mapping is somehow continuous or something like that. I'll say more about that in a second. Okay, the way that this works is that there's a series of key reductions here. So I'll show you how the mixture oracle allows us to learn the bipartite graph between the latents and the observables. And in fact, you don't need the full power of the mixture oracle. All you need is to figure out the orders of the induced mixture models. From the bipartite graph and the mixture oracle, you can then, I will show you, learn the latent distribution over the hidden variables. And from here, I claim it's sort of a well-studied problem to figure out the causal graph. So you make some identifiability assumption. It could be faithfulness, it could be a lingam, it could be equal variances, whatever you like. Once you know this latent distribution, this reduces, learning the causal graph reduces to a fully observed causal discovery problem. So I'm going to focus on the first two problems because these are sort of the new interesting parts. And so, for example, in our experiments, we just ran GES using P of H and got good results. Yeah.
So just a question. So the distribution P of H will be a distribution over discrete variables, right?
Yes, that's correct. Yes.
So lingam just wouldn't apply.
Sorry, yeah, I shouldn't have said lingam. Yeah, you're right.
So what would apply?
I mean, you could assume faithfulness, for example, and then you could learn the Markov stuff.
Oh,
Sure.
so then just the equivalence class.
Sure. Yes. So that's like sort of my perspective on this is that once you know P of H, you make assumptions to identify as much as you want about that graph, whether it's the equivalence class or something more specific than that. Yeah, no, that's a good question. Okay, so I'm going to focus on the first two parts. Okay, so how do we learn this bipartite graph? So there's a lot buried in here, but the basic idea is the following. We're going to use the number of components for subsets of size at most 3 to construct a tensor. And this tensor, its decomposition will correspond to the columns of A. And under the assumption that the columns of A are linearly independent, this tensor will have a unique decomposition, and you can apply standard algorithms like Yanrick's algorithm to figure out the columns of A and hence the bipartite graph. Yes.
So is this an assumption on the measurements?
Is what
Linear independence.
This is an assumption on the relationships between the hidden variables and the observed.
Okay.
Yeah.
So it's in addition to the assumption on the non-inclusion.
Yeah. So in order for this step to work, you need the columns to be linearly independent. Yeah. Okay. So that's how you identify the bipartite graph. Now notice the bipartite graph is not really what I'm interested in, but it's sort of an interim step that I need for the next step, which is to learn the latent distribution itself. And so this algorithm is fairly complicated, but let me kind of give you a little bit of a picture of how this works. So there's sort of a hidden magic to the mixture oracle assumption that I haven't emphasized yet. So if you think about the mixture oracle assumption, if I look at the mixture model over all of the variables, the weights in that mixture model correspond exactly to the entries of the joint probability table of H. But what the mixture oracle doesn't tell me is which weight corresponds to which entry or which states in the hidden variables. So essentially what we need to do now is figure out how to assign probabilities or weights to states, to hidden states. That's the name of the game. So the full mixture gives us the probabilities. And then what the bipartite graph is going to do is it's going to allow us to exploit the Markov property to understand when I change a hidden variable, which observables could possibly change. So the way you can think about this is I take the joint probability table of H, I shake it up, I throw it into a bag. And the way the algorithm works is I pluck out a random, any probability, it doesn't matter. And I'll assign it, let's say, to like all zeros. And then I'm going to start changing a single hidden state, one state at a time. And then I'm going to be able to rule out via the Markov property certain states. And then I'm going to keep doing this inductively until I'm able to isolate sort of the last state that corresponds to a probability and then work my way backwards. So there's some careful bookkeeping here, but this runs in time. So what is this? So this is the number of hidden variables, the number of hidden variables H, the number of observed variables X, and K, capital K here is the total number of hidden states, okay? So of course, you need at least order K time for this algorithm to run. Okay, so this gives us the latent distribution P of H. And from here, I can run, again, let's say greedy equivalent search to learn the latent DAG if I want to. Okay, and I'll show you some examples of that in a second. But first, I want to talk a little bit about, oh, yeah, go ahead, Dan.
Yeah, can I just ask real quick?
Yeah.
So you're not restricting anything about the state space of H. You're just saying it's discrete.
Mm-hmm.
And so if I gave you some H, if I thought I found some H's that were things where I had, they took on 3 different values, like 0, 1, 2, and then I replaced it with H, a smaller number of H's that just took on binary values. So I can like sort of, what's preventing that kind of procedure from resplitting by sort of adding more H's with less complicated state spaces or fewer H's with more complicated state spaces?
Okay, so just to be clear, I want to make sure I understand. So you're saying, like, for example, I can imagine I have like a mixture of 3 components, and then I'm going to take 2 of them, merge them together, and say like that's one component, and then I have the other, right? This is the mixture oracle assumption. However, notice that in order for H to be identifiable itself, you need to be able to identify these components, right? So I'm going to talk a bit more about exactly how we would actually figure out specifically your question here, but this boils down to the mixture identifiability assumption. If basically what you're saying is there's a setting where maybe the mixtures aren't identifiable, in which case this problem is impossible. Yeah. Does that kind of make sense?
Yeah, I think so. So are you going to specify when you actually run, if you were to run this procedure, would you specify the number of H's and the no,
you will not specify.
You have linear independence of the columns. It's the linear dependence of the columns of your measures.
Actually, this is a good point. So the only issue is, so you're right, but the only issue is I can't even get there until I've used the mixture oracle already. So that's one. So I'm already using the fact that the mixture is identifiable, which solves Dan's question. But you're right, that in linear independence would also save you at that point. Yeah. Okay. So yeah, but let me. So this is a great segue. So this is like the fundamental question. When you're looking at mixtures, how do you know you have 3 or 2 components? So, for example, if you wanted to make a parametric assumption that all of these conditional distributions were, say, Gaussian, this problem would go away. Gaussian mixtures are identifiable. We would not have to worry about this. Okay, so let me talk a little bit about that and then how we do this in the non-parametric setting. Okay, so let me take a step back from the graphical model setup and talk about general mixture models, which I should point out is an example of it's a special case of my model with just a single latent variable. So I will write this mixture model that you saw before, maybe in a way that's more familiar to those of you that might have worked on mixture models. It's just a convex combination of some densities. You do not need these to be densities. They could be measures if you want, but let's stick to densities. And the previous discussion we just talked about, if we make no additional assumptions on these densities, then things are not identifiable. We're in trouble. Okay, so let me be very clear what I mean by identifiability here. So I can, given any mixture model, I can define what's called the mixing measure, capital Omega here. And what it is a convex combination of point masses concentrated on the densities that this mixture we're taking a convex combination over. And identifiability for me means that the map that takes this mixing measure to this mixture distribution defined up here is injective, it's 1-to-1. So this is different from the perspective that Leonard and Yuval took previously in the week, where what they want, if I understood, and please correct me if I'm wrong, was that this map was somehow continuous. There was a continuous dependence between omega and the distribution. Here, I'm only insisting on identifiability. If you want to be able to estimate this, then you want this to be continuous somehow. That's sort of the crucial thing. Okay, so as I alluded to previously, if this family script f is parametric, so Gaussian, exponential random families, there's lots of other examples. Not only do you get identifiability as I've defined up here, you also get polytime algorithms, sample complexities, lots of good stuff, right? That's basically what the parametric setting gets you. So what I want to focus on in the last few minutes of this talk is what about non-parametric sets of conditional distributions? Okay, so I sort of hid something here. I was talking about this set script f, but for the statisticians in the audience, you'll notice that this is not really how I've parametrized this model. This model is parametrized via omega. So instead of placing assumptions on f, I could ask myself what happens if I place assumptions on omega. So it turns out that you can avoid putting really any assumptions on f by putting the right assumptions on omega. In other words, your mixing measures have to be well behaved in a specific way. And what does that look like? So in a paper from a couple of years ago, we proved that as long as the distance between any two of your components is separated, it's lower bounded by a number that depends on omega. Okay, so that's crucial here. Then you can identify this mixture model and you can also estimate it. So this is sort of, so Dan, to your question, basically the idea is we're enforcing some minimum separation, and the separation depends on what else is in the mixture. And so as long as things are well separated, you can sort of, the idea is that you can point it out and say, oh, there's 1, 2, 3 components here. Okay. All right, so in the original paper, we showed that there was a pointwise consistent estimator. For those of you that are interested in the finer details of this, it turns out that there does not exist a uniformly consistent estimator in general, but if you add additional regularity conditions, you can show in a paper that we put out last year that you can in fact get uniformly consistent estimators. And really the interesting thing here, so for those of you that are interested in sample complexities, so let me go back to the Gaussian mixture model for just a second. Yeah, go ahead.
Is that assumption the fi, fj are functions of omega?
These are the densities. Sorry, these are just the density. These are the component densities in your mixture model.
But like the assumption is posed on omega, but are you assuming you can read out fi, fj from omega?
Oh yeah, absolutely. That's just because omega is literally defined as a.
That itself require identifiability.
I mean, if you know omega, you can read off, right? But so identifiability would say if I gave you this thing, you could tell me that Fi and the Fj. This assumption is simply saying that given omega, I'm going to put an assumption on omega, but I'm not saying this assumption isn't assuming that you can recover omega from the joint distribution to begin with. Yeah, no, that's a good clarifying question. Yeah. Okay, so back to the Gaussian mixture model setting. So there exist polytime algorithms for learning Gaussian mixture models, but there's a catch to these. So yeah, oh, okay. Thought you were waving at me. The catch is the dependence on the number of components in the mixture is exponential. So you can get polytime algorithms, but there are exponential lower bounds on the number of components. And so sort of mixture models are usually considered one of these difficult models due to these lower bounds. So also in terms of non-parametric estimation, we know that there's an exponential dependence on the dimension in terms of non-parametric density estimation. Now, what I claim is that for this problem, if you restrict the number of components to be 2, and you know that, and you only look in one dimension, then this problem is fundamentally hard in the sense that there is no polynomial time algorithm that will solve this. So this has nothing to do with number of components. It has nothing to do with the curse of dimensionality. Simply deconvolving 2 non-parametric densities under the assumption that they're identifiable is a fundamentally hard problem, and there's no polynomial time algorithm.
Now, this is a question. Was that like given enough samples, it's not polynomial time algorithm, or is it that I need super polynomial many samples?
It's a sample result. Yeah.
Okay.
Yeah, you're gonna. Yeah, that's how we prove this. Yeah. Okay. And I guess maybe to point out one last thing regarding the identifiability. So I was talking about how you can get identifiability when things are separated. I just want to point out that the separation is in distribution space, not in like space, like in space, I guess. So here's an example over here. The purple distributions here, think of this as one component, and the green is another component. So they perfectly overlap. They have the same first moments, and this is identifiable because these are distinguishable in distribution space. So in other words, their higher order moments are very different. So you don't actually, this is not like a clustering type thing. This really just depends on the properties of the distribution. Okay, so last thing I wanted to say, so I don't go into all the practical details of how we do this, but everything I just showed you can in fact be practically implemented. So I'll add the caveat that, for example, for learning the latent causal graph, this is restricted to relatively small graphs due to the computational complexity. But it is actually practically implementable. And if you focus on the blue bars here, this is the Hamming distance between the true graph and the learned graph. So we implemented this algorithm using k-means to implement the mixture oracle. So we didn't have to do anything super fancy. It turns out k-means will do a good job. And then we used greedy equivalence search to learn the Markov equivalence class. And then over here on the right, I always like to show this fun picture of an example where we learned a non-parametric mixture model with 6 components. Yes, 6 components. Right? Any questions so far? So one of the sort of interesting questions would be to develop finite sample efficient algorithms for these types of problems. And that is one of the open questions here. So, oh yeah, no, go ahead. Yeah.
Which bit of this is A or B that means that it's computationally difficult?
So if you're referring to the non-parametric part that I was talking about on the previous slide, it's part A. It's the mixture oracle that makes this hard. I mean, let's be clear, B is also very hard. But yeah. Okay, so yeah, go ahead.
When you say you don't have a finite sample complexity, does this simply mean that you're working with the exact statistics?
Yes, exactly. Yes, that's exactly. So let me just be very clear. This theorem is, yes, this is assuming access to the exact marginal over X. But these results, these are finite sample and asymptotic sample results. Okay. Yeah. Okay. So any other questions? All right, let me wrap up real quick. So We talked about non-parametric identifiability in latent causal models, and sort of the crucial things. So the two takeaway messages are this reduction to two well-studied problems of causal discovery and mixture models. And the fact that sort of what originally motivated this was trying to understand necessary and sufficient conditions for this problem. So I think we made sort of some good steps in that direction, but there still remain many open questions regarding the necessary and sufficient conditions here. So for example, so one big question is it possible to actually avoid using this mixture oracle? It's clearly sufficient. If your model is identifiable, you have access to such an oracle. It does not mean you have to use it. So one question is if it's possible to avoid it. An obvious question for the causal inference folks is what if I want to allow edges between the observables? This is a setting that would allow me to start considering some interesting problems involving confounding. And then I already mentioned this, but sample and computational complexity questions for these algorithms. So I think I'm a little over time. So I'd like to just thank all my amazing collaborators and the students that worked on this with me. If you're interested in looking at any of these papers, they're available online. I'll finish there.
And so we have time for a question here. There's one in the audience here. Richard, yes.
Yeah, thanks for a great talk. I just want to understand, is there any case that, I mean, I was just wondering if there can be a reduction that you can assume without loss of generality, all the latents are exogenous, meaning there's no errors between them.
So there are some results of this nature, but then, so like the setting that I'm interested is where you're actually interested in the relationships between the latents, right? So those reductions would violate the assumptions that I have that I've made here.
Which assumptions that would
off the top of my head, I don't know. But that would be an interesting question. So basically, like one way to think about this is if you want to reduce it to that case, then you have to just have one variable or a bunch of, it has to be that there's a bunch of independent variables somehow. So yeah, but it would be interesting to actually compare those reductions and see what goes wrong.
Great. Well, let's thank Bryon one more